Hello, and welcome to Lesson 5 of the Big Data and Hadoop Developer course offered by Simplilearn. This lesson will introduce you to MapReduce and its operations. Let us explore the objectives of this lesson in the next screen. By the end of this lesson, you will be able to explain the concepts of MapReduce, list the steps to install Hadoop in Ubuntu machine, explain the roles of user and system. In the next screen, we will have an introduction to MapReduce. MapReduce is a programming model. It is also an associated implementation for processing and generating large data sets with parallel and distributed algorithms on a cluster. MapReduce operation includes specifying the computation in terms of a map and a reduce function. It makes parallel the computation across large-scale clusters of machines. MapReduce handles machine failures and performance issues. It also ensures efficient communication between nodes performing the jobs. Computational processing can occur on data stored either in a file system, namely unstructured data, or in a database, namely structured data. MapReduce can be applied to significantly larger data sets when compared to commodity servers. In the next screen, we will understand MapReduce with an analogy. The MapReduce steps are illustrated on screen using manual vote counting after election as an analogy. Step 1. Each poll booth's ballot papers are counted by a teller. This is a pre-MapReduce step called input splitting. Step 2. Tellers of all booths counts the ballot papers in parallel. As multiple tellers are working on a single job, the job execution time will be faster. This is called the map method. Step 3. The ballot count of each booth under the Assembly and Parliament seat positions is found, and the total count for the candidates are generated. This is known as the reduce method. Thus, map and reduce will help in the quick execution of the job when compared to individual counting. In the next screen, we will continue to discuss the analogy. The analogy given in the previous screen helps in understanding the usefulness of MapReduce. The key reason to perform mapping and reducing is to speed up the job execution of a specific process by splitting a process into a number of tasks, thus enabling parallelism. If one person counts all the ballot papers, or has to wait for another to finish the ballot count, it might take a month to receive the election results. In such a case, we may receive the election results after a month. When many people count simultaneously, the results are obtained in a day or two. This is how MapReduce works. In the next screen, we will understand MapReduce operation through an example. In this screen, the MapReduce operation is explained using a real-time problem. The job is to perform a word count of the given paragraph. The paragraph is, "This quick brown fox jumps over a lazy dog. A dog is a man's best friend." The MapReduce process consists of input, splitting, mapping, shuffling, and reducing phases. The input phase refers to providing data for which the MapReduce process is to be performed. The paragraph is used as the input here. The splitting phase refers to converting a job submitted by the client into a number of tasks. In this example, the job is split into 2 tasks. The mapping phase refers to generating key-value pair for the input. Since this example is about counting words, the sentence is split into words by using the substring method to generate words from lines. The mapping phase will ensure that the words generated are converted into keys, and a default value of 1 is allotted to each key. The shuffling phase refers to sorting the data based on the keys. As shown on the screen, the words are sorted in ascending order. The last phase is the reducing phase. In this phase, the data is reduced based on repeated keys by incrementing the value. The word dog and the letter A are repeated. Therefore, the reducer will delete the key and increment the value depending on the number of occurrences of the key. This is how the MapReduce operation is performed. In the next screen, we will understand map execution. Map execution consists of 5 phases: map phase, partition phase, shuffle phase, sort phase, and reduce phase. Click each tab to know more. In the map phase, the assigned input split is read from HDFS, where a split could be a file block by default. Further, input is parsed into records as key-value pairs. The map function is applied to each record to return 0 or more new records. These intermediate outputs are stored in the local file system as a file. They are sorted first by bucket number, then by key. At the end of the map phase, information is sent to master node of its completion. In the partition phase, each mapper must determine which reducer will receive each of the output. For any key, regardless of which mapper instance generated it, the destination partition is the same. Please note that the number of partitions will be equal to the number of reducers. In the shuffle phase, input data is fetched from all map tasks for the portion corresponding to the reduced tasks bucket. In the sort phase, a merge sort of all map outputs happens in a single run. In the reduce phase, user-defined reduce function is applied to the merged run. The arguments are key and corresponding list of values. The output is written to a file in HDFS. In the next screen, we will understand map execution in a distributed 2-node environment. The diagram on the screen depicts the MapReduce execution in a distributed 2-node environment. The mappers on each of the nodes are assigned an input split of blocks. Based on the input format, the record reader shown as RR in diagram reads the split as key, value pair. The map function is applied to each record to return 0 or more new records. These intermediate output are stored in the local file system as a file. Thereafter, a partitioner assigns the records to a reducer. In the shuffling phase, the intermediate key, value pairs are exchanged by all nodes. The key, value pairs are then sorted by key and reduce function applied on it. The output is stored in HDFS based on the specified output format. In the next screen, we will discuss MapReduce Essentials. The essentials of each MapReduce phase are shown on the screen. The input to a job is an input specification that is in key-value pairs. Each job consists of 2 stages. First, a user-defined map function is applied to each input record to produce a list of intermediate key-value pairs. Second, a user-defined reduce function is called once for each distinct key in the map output and passed the list of intermediate values associated with that key. The number of reduced tasks can be defined by the users. Each reduced task is assigned a set of record groups, that is, intermediate records corresponding to a group of keys. For each group, a user-defined reduce function is applied to the record values in that group. The reduced tasks read from every map task, and each read returns the record groups for that reduced task. Please note that reduce phase cannot start till all mappers have finished processing. In the next screen, we will study MapReduce jobs. A job is a full MapReduce program, which typically will cause multiple map and reduce functions to be run in parallel over the life of the program. Many copies of map and reduce functions are forked for parallel processing across the input data set. A task is a map or reduce function executed on a subset of data. With this understanding of job and task, The job tracker and task tracker functions will be easy to comprehend. Job tracker schedules and manages MapReduce applications, also known as jobs. The job tracker runs on a separate node and accepts job requests from the client. It divides job requests into tasks, schedules, and assigns tasks to slave nodes and is a single point of failure. A task tracker manages each active task and communicates regularly with job tracker. In the next screen, we will understand MapReduce Engine. Two essential services that are responsible for performing MapReduce operations are the job tracker and the task tracker. Generally, the job tracker is present in the master node of the Hadoop setup with the name node service, whereas the task tracker service is present in the slave nodes along with the data node service, as shown on the screen. The job tracker service is responsible for assigning jobs to the data node. The data node consists of the task tracker, which performs the tasks that are submitted by the job tracker and provides the results back to the job tracker. In the next screen, we will discuss the associated tasks of MapReduce. Some MapReduce and associated tasks are listed on screen. The map process is an initial step to process individual input records in parallel. The reduce process is all about summating the output with a defined goal as coded in business logic. Task trackers keep track of individual map tasks and can run in parallel. A map job runs on a particular task tracker slave node. The job tracker keeps track of a MapReduce job. Periodically, it communicates with task trackers to get the status of the job progress. It allocates a map task to a particular task tracker node. Like the name node server, this is another master process that is very critical with one instance running per Hadoop cluster. In the next screen, we will discuss the Hadoop job flow. This screen shows how MapReduce-Processes relate to HDFS nodes in a cluster. Here is one possible configuration. The job tracker and name node share the same node in this topology, although that doesn't necessarily need to be the case. The slave nodes store and manage HDFS data. That is, they are the data nodes. The slave nodes run MapReduce tasks as directed. That is, they support the task tracker process. In the next screen, we will discuss the MapReduce job interactions. The flow diagram shown in the screen represents the Hadoop job flow interaction. Click each tab to know more. Initially, a Hadoop MapReduce job is submitted by a client in the form of an input file or a number of input split of files containing data. After being submitted by the client, the job is under the control of the job tracker. The job tracker distributes the input, split to separate task trackers. It also coordinates with multiple task trackers residing in a single cluster. The job tracker then resubmits the task to alternate task trackers if the data node fails. The job tracker gathers the final output and informs the client of the success or failure status. In the next screen, we will list MapReduce characteristics. Some MapReduce characteristics are listed on screen. MapReduce is designed to handle very large-scale data in the range of petabytes, exabytes, and so on. It works well on write once and read many data, also known as worm data. MapReduce allows parallelism without mutexes. The map and reduce operations are typically performed by the same physical processor. Operations are provisioned near the data, that is, data locality is preferred. Commodity hardware and storage is leveraged in MapReduce. The runtime takes care of splitting and moving data for operations. In the next screen, we will list some real-time uses of MapReduce. Some of the real-time uses of MapReduce are listed on the screen. These include simple algorithms such as grep, text indexing, and reverse indexing. Data-intensive computing, for example, sorting are also good candidates for MapReduce. Data mining operations like Bayesian classification use this technique. Search engine operations like keyword indexing, ad rendering, and PageRank have been regularly using MapReduce, and so is enterprise analytics. Gaussian analysis for locating extraterrestrial objects in astronomy have found MapReduce a good technique. There seems to be good potential for MapReduce in semantic web and Web 3.0. In the next screen, we will study Hadoop installation in Ubuntu. Ubuntu Desktop 12.04 VM installed with Eclipse and a high-speed internet connection is required to install Hadoop in Ubuntu Desktop 12.04. In the next screen, we will list the steps to get the VM ready for Hadoop MapReduce programming. The steps required to install Hadoop in Ubuntu Desktop 12.04 LTS are given in the screen. Create a new VM and install Ubuntu Desktop 12.04 LTS operating system. Install all Hadoop features in pseudo-distributed mode. Start all Hadoop services. Install Eclipse from Ubuntu Software Center. Add all essential jar files to run MapReduce code. Finally, run a sample code to ensure that the environment settings are correct. In the next screen, we will discuss a business scenario to understand how to upload big data in Hadoop, install Eclipse, create projects, and write simple MapReduce programs. Olivia is the EVP of IT Operations with Nutra Worldwide Incorporated, and Tim Burnett, the AVP of IT Infra Ops, is assigned to one of her projects. Olivia has asked Tim to analyze 2 large data sets and set up mock activities for anyone new to MapReduce. One of the data sets includes a novel and the other one includes a weather report for a city. Tim wants to install Eclipse on his system to create a new project to run default MapReduce programs. Some of the MapReduce programs that he wishes to run include counting the words from a paragraph and finding average temperature. The demos in this module will illustrate how to install Ubuntu Desktop OS, install Eclipse, create projects, and write simple MapReduce programs. In the next screen, we will set up the environment for MapReduce to ensure that all Hadoop services are live and running. This can be verified by using the command JPS and looking for all 5 services, namely name node, data node, task tracker, job tracker, and secondary name node. In the next screen, we will refer to some sample data to work on MapReduce development. An important question is from where we can get the big data and small data required to perform processing and MapReduce operations. For example, we will use the War and Peace book and climate data, that is, weather data, on an hourly basis. These can be downloaded from the URL shown on the screen. The sample data set will be provided and can be used to perform MapReduce operations. In the next screen, we will upload small data and big data to HDFS. The command to upload any data, big or small, from the local system to HDFS is Hadoop space fs space hyphen copy from local space source file address space destination file address. The command to upload small or big data is shown on the screen. In the next screen, we will view a demo on uploading a file to HDFS. This demo will help you upload small data and big data to HDFS. Select Install Ubuntu. Click the Continue button. Click the Continue button. Click the Install Now button. The file copy process starts. Click the Continue button. Click the Continue button. Enter the password. Retype the password. Click the Continue button. The installation process starts. Click the Restart Now button once the installation is complete. Thus, we have successfully installed Ubuntu Desktop. Let us do a quick recap of the steps performed. The steps to build a MapReduce program are listed on the screen. Determine if the problem is parallelizable and solvable using MapReduce. For example, is the data write once, read many, or worm in nature, or do you have a large data set? Further, design and implement solution as mapper classes and reducer class. Compile the source code with Hadoop core and package the code as jar executable. Configure the application job as to the number of mappers and reducers tasks, input and output streams. Load the data or use it on previously available data. Launch the job and monitor. Study the result. In the next screen, we will discuss MapReduce requirements. The user or developer is required to set up the framework with the following parameters: the locations of the job input in the distributed file system, the locations of the job output in the distributed file system, the input format, the output format, the class containing the map function, optionally the class containing the reduce function. If a job does not need a reduce function, there is no need to specify a reducer class. The framework will partition the input, schedule, and execute map tasks across the cluster. If requested, it will sort the results of the map task and execute the reduced tasks with the map output. The final output will be moved to the output directory, and the job status will be reported to the user. In the next screen, we will discuss the features and process of MapReduce. MapReduce functions use key-value pairs. Some of the key features of Hadoop MapReduce function are as follows. The framework converts each record of input into a key-value pair, which is a one-time input to the map function. The map output is also a set of key-value pairs, which are grouped and sorted by keys. The reduce function is called once for each key, in sort sequence, with the key and set of values that share that key. The reduce method gives an output as an arbitrary number of key-value pairs that are written in the output files in the job output directory. In the next screen, we will explore the processes of Hadoop MapReduce. The framework provides two processes that handle the management of MapReduce jobs. They are the Task Tracker and Job Tracker services. The Task Tracker service resides in the data node. The Task Tracker manages the execution of individual map and reduce tasks on a compute node in the cluster. The Job Tracker service resides in the system where the name node service resides. The Job Tracker accepts job submissions, provides job monitoring and control, and manages the distribution of tasks to the Task Tracker nodes. In the next screen, we will explore the steps of Hadoop MapReduce. The image shows the set of classes under User Supply and the Framework Supply. User Supply refers to the set of Java classes and methods provided to a Java developer for developing Hadoop MapReduce applications. Framework Supply refers to defining the workflow of a job, which is followed by all Hadoop services. As shown in the image, the user provides the input location and the input format is required by the program logic. Once the job tracker accepts the input, the specific job is divided into tasks, and each task is assigned to an individual task tracker. Once the assignment is complete, the task tracker will start the map task. It performs shuffling, partitioning, and sorting for individual map outputs. Once the sorting is complete, the reducer starts the merging process. This is also called the reduce task. The final step is collecting the output done once all the individual tasks are reduced based on program logic. In the next screen, we will discuss the responsibilities associated with the MapReduce process. The basic user or developer responsibilities of MapReduce are setting up the job, which is usually done by the job tracker, specifying the input location, and ensuring the input is in the expected format and location. The user or developer is also responsible for ensuring that the output is in the expected format and location. The framework responsibilities are distributing the job among the task tracker nodes of the cluster, running the map operation, performing the shuffling and sorting operations, reducing phases, placing the output in the output directory, and finally informing the user of the job completion status. In the next screen, we will set up Hadoop in the Ubuntu Desktop 12.04 LTS operating system. To install Eclipse in the Ubuntu Desktop 12.04, open Ubuntu Software Center and type Eclipse in the search bar, as shown on the screen. Select Eclipse in the listing and click the Install button to continue. In the next screen, we will discuss the steps required to create a new project in Eclipse for MapReduce development. Create a new project and add the essential jar files to run MapReduce programs. To create a new project, click the File menu and select New Project. Alternatively, press Ctrl+N to start the wizard of the new project. In the next screen, we will continue to discuss the steps to create a new project. Select Java Project from the list and click the Next button to continue. In the next screen, we will continue discussing the steps to create a new project. Type the project name, for example, word count, and click the Next button to continue. In the next screen, we will continue discussing the steps to create a new project. Include jar files from the Hadoop framework to ensure the programs get all the dependencies at one location. In the next screen, we will continue discussing the steps to create a new project. Under the Libraries tab, click the Add External Jars button to add all the essential jar files. After adding all the jar files, click the Finish button to create a project successfully. In the next screen, we will have a demo on installing Eclipse in Ubuntu Desktop. Here is a demo on installing Eclipse in the Ubuntu Desktop. Open -Home. Search for Ubuntu Software Center. Click the Ubuntu Software Center icon. On the search bar, type Eclipse and press Enter. Select Eclipse from the list and click the Install button. You will be asked to enter password. Enter correct password and click the Authenticate button to install Eclipse. Time taken to install Eclipse will depend on the internet speed. Thus, we have successfully installed Eclipse in Ubuntu Desktop. Let us do a quick recap of the steps performed. Here is a demo on creating a new project and adding external jar files on Eclipse in the Ubuntu Desktop 12.04 LTS. Ensure that Hadoop services are running. Type JPS and press Enter. Upload the data in HDFS. Type the command shown on the screen and press Enter. Start Eclipse. Click New and select Project from the menu items. Press Enter to continue the process. Select Java Project and click Next. Type the project name as word count and click Next. Click the Libraries tab. Click the Add External Jars button and add all jar files present in the location /usr/local/Hadoop and /usr/local/Hadoop/lib. You will see a dialog box stating Open Associated Perspective. Click the No button to continue. Thus, we have successfully created a project to run MapReduce Java application. Let us do a quick recap of the steps performed. It is essential to check whether the machine setup we created can perform MapReduce operations. To verify this, we need to use the example jar files deployed by Hadoop. This can be done by running the command shown on screen. Before executing this command, you need to ensure that the words.txt file resides in the /data/first location. In the next screen, we will view a demo for running the first MapReduce application using Hadoop-examples.jar file. Here is a demo to run the first MapReduce application using Hadoop-examples.jar. Ensure that all Hadoop services are running. Type JPS and press Enter. Let's check an example of using Hadoop default example jar files. We will find the value of pi. Type the command shown on the screen where the first 10 stands for mapper and the second 10 stands for reducer. Press Enter to execute the command and view the output. Thus, we know how to execute a jar file to perform MapReduce operation. Let us do a quick recap of the steps performed. Here is a demo of wordCount.java to run in the first MapReduce application using Eclipse. Ensure that Hadoop services are running. Type JPS and press Enter. Upload the data in HDFS. Type the command shown on the screen and press Enter. Start Eclipse. Click New and select Project menu item. Press Enter to continue the process. Select Java Project and click Next. Type the project name as word count and click Next. Click the Libraries tab. Click the Add External Jars button and add all jar files present in the location /usr, /local, /Hadoop, and /usr, /local, /Hadoop, /lib. You will see a dialog box stating Open Associated Perspective. Click No to continue. Right-click on the word count project. Select New and select Class. Type the desired class name. Here we will type word count. Click Finish. The Java file opens. Open the sample code file and copy the code. Paste the code in Eclipse. Run the code by clicking Play. You will get an error. Right-click on the class file and click the Properties menu item. Click Run Debug Settings. Select Class Word Count and click Edit. Click the Arguments tab. Type the input location HDFS : /192.168.21.181:1001/data /war_and_piece.txt. Type the destination location, that is, HDFS: /192.168.21.181:data/small/output1. Click the Terminal option. Click Apply. Click OK. Run the program by clicking Play. You will observe that MapReduce operation will start. To verify the output, open web browser and navigate to http://192.168.21.181:50070. Go to the output location. you will find a file called part-0000. Click the file and see the output. Thus, we have successfully executed the program. Let us do a quick recap of the steps performed. Here is a demo to run a program and find the average temperature in the month of January 2012 using big data. Open Termina. Ensure Hadoop services are active using the command jps. Start Eclipse and create a new workspace. Click OK to continue. Eclipse starts with a welcome screen. Click on Workbench. Let's create a project. Click on File menu and go to New menu item. Click the Project menu item. Select Java Project and click Next. Give project a name. For example, average temperature. Click Next, select Libraries tab. Click Add External Jars button. Navigate to Hadoop location at /usr/local/Hadoop. Select all the jar files and click OK. Click Add External Jars. Double-click the lib folder. Select all the jar files and click OK. Click Finish. Click No. Your project is created successfully. Right-click on the project. Select New. Select Class. Give class name as Average Temperature and click Finish. Follow the same procedure for Average Temperature Mapper and Average Temperature Reducer. Open the source code file provided. Copy the source code and paste it in Eclipse under AverageTemperature.java. Open AverageTemperature-Mapper.java file and copy the source code. Paste the source code in the Eclipse under the tab AverageTemperature-Mapper.java. Open AverageTemperature-Reducer.java and copy the source code. Paste the source code in the Eclipse window under the tab AverageTemperature-Reducer.java. Right-click on the project and select Properties. Click Run Debug Settings. Click New. Select Java Application and click OK. Open Arguments tab. Enter the HDFS location of the data as HDFS:192.168.201.181:data/big/data/201.201 hourly.txt. Press Enter and type the destination location of output as HDFS:192.168.201.108.1.1001/data/big/output1. Click Apply. Click OK. Click Apply. Click OK. Execute the program by clicking Play. The MapReduce operation will start. Go to Data Location in Name Node GUI for verifying the output. Click the big link. Click the Output To link. The output is generated successfully. Click the part-00000 file. The output shows the average temperature at the following dates. We have successfully executed the program. Let us do a quick recap of the steps performed. This screen shows the MapReduce v2.0 architecture comprising of Yarn. Let us summarize the topics covered in this lesson. MapReduce involves processing jobs using the batch processing technique. MapReduce can be done using Java programming. Hadoop provides with Hadoop examples jar file, which is normally used by administrators and programmers to perform testing of the MapReduce applications. MapReduce contains steps like splitting, mapping, combining, reducing, and output. In the next lesson, we will learn advanced HDFS and MapReduce.